Yeah, thank you very much for the introduction, and of course, thank you to James and Ankit for inviting me and to this really very nice workshop, I must say, and also for trusting me to give this tutorial, which I think other people in the room might probably be even much better suited to. But anyway, so this is not the title of my talk, but the title I choose for the tutorial of this session, quasi-steady non-thermal phases. And we know that if you do a pump-probe experiment, then usually you expect that usually the system quickly returns back to the equilibrium state, and this is also what the pump-probe experiment relies on, but there are notable cases in which this is not the case. Like, for instance, you have this experiment in a system with intertwined orbital and magnetic orders where like the laser excitation quickly drives it to ordered states which are distinct from the ones which you reach by thermal protocols, and this has been called hidden states. And there's another observation of a set of hidden states which are reached on ultra-fast timescales in this material tantalum disulfide, where a single laser pulse can switch the material from insulating to metallic behavior, also to amorphous-like states, and I think we will have a talk on this right after me, so I don't have to talk much about this. And also the observation of possible light-induced superconductivity in this K3C60 compounds is actually a long-lived phenomenon which can be observed on an almost nanosecond timescale, which is quasi-infinite on the electronic timescale. Yeah? So I think from my perspective, it's fair to say that these are kind of accidental findings. We don't have a real systematic understanding how we come to these long-lived states, and as I understand, this is also one of the goals of this workshop, to identify the pathways to do this. So what this tutorial is aimed, or what I thought I could do, is put some theory perspectives on a few generic mechanisms which give rise to long-lived states. And in this context, by long-lived, I thought I'm not only referring to metastability, which is really almost infinite lifetime, but to something which on a certain timescale can be understood as a quasi-stationary picture. Yeah? This is my concept of long-lived for this tutorial. So the general viewpoint would be that I excite the system, and on some pathway it will approach the thermal state. So but on the way towards it, it is close to a non-equilibrium stationary state. And this situation, that you have a close passage to such a state, has some context also be called, or this state here, this hypothetical really stationary state, has been called a non-thermal fixed point of the dynamics. Yeah? So let's also be expressed, what I'm discussing is all states during the relaxation. They're no longer driven while they relax. And a completely different and interesting question would be, of course, whether you can reach stationary states while you drive them, such as Floquet states and so on. Yeah, so if you ask me whether I can try to categorize these non-equilibrium stationary state or non-thermal fixed points, I think there are three types which I would like to discuss. One would be what I would call pre-thermal type fixed points. One would be dissipative driven states, and one would be classical metastability. So let me say a few words on each of these. So the pre-thermalization, the notion of pre-thermalization comes from high energy physics. The term was developed in context of heavy ion collisions. I would generally view this as a quasi-stationary state that arises due to constraints in the dynamics. Constraints which correspond to conservation laws. Yeah? And where this is mostly discussed is in the context of integrable or weakly integrable system, where an integrable quantum system is one that actually has an infinite set of constants of motion, which are analytic objects, yeah, and not just the energy and particle number. And if you excite such a system, for instance, by preparing a non-equilibrium initial state and let it evolve, which is called a quench, then all these quantities will be conserved. And the best the system can do is to come to a state which maximizes the entropy given all these constraints. And that's a Gibbs ensemble which has a generalized chemical potential for each of these conserved quantities. Yeah? And this is, as I said, discussed in called for truly integrable system. Like in real life, you will always have a perturbation of this integrable Hamiltonian. And then the general concept is that on a transient time scale, you would go to a state, quickly go to a state that's very close to this steady state of the integrable point, and then the perturbations would finally, on a longer time scale, drive you to a thermal state. So here's just one illustration, which is the simplest case also from condensed matter physics. It's a weakly interacting Fermi system. So you can imagine that you prepare a Fermi sea and then let the system evolve. It's interacting, so it will go to a thermal equilibrium distribution where the final momentum distribution is a Fermi distribution. You can imagine that you follow for each of these momenta the evolution, and which goes then from this initial state where like all these would be 0 to a final one where they have this thermal one. But then you see that the dynamics undergoes like a quick relaxation to something which is not the initial state, but also not the thermal state, but then on a much longer time scale. So note this is logarithmic, goes to final state. So this is an actual simulation here for a quench in the Hubbard model, but whatever. Yeah. So this particular type of pre-thermal behavior may not be so relevant for like our experiments, because like the physics which drives it to the thermal state is basically quasi-particle scattering, which we know in most metals, which would correspond to this weakly interacting Fermi system. This is still femtoseconds, so like this is a short time. But you can ask of, and this is not what I discuss here, but like pre-thermal situations in other degrees of freedom, such as Magnon or like bosonic distributions, or like, and this is what I will discuss a bit later, other types of bottlenecks that give rise to constraints. In particular, bottlenecks that are due to a gap in the system, and the cases will be one in which I call photodoped states, where you excite electrons over a gap and then they can relax slowly back. So the constraint would be the occupation, say, in the upper band, or in a context of a Hubbard model, the number of charge excitation. And in particular, this is interesting if the gap is due to a symmetry-broken state, because then you can ask whether the symmetry-broken state itself like helps to have the gap helps to survive. So this would be pre-thermal fixed points. Now, the other set are dissipative-driven states as a fixed point. So a dissipative steady, non-equilibrium steady state is, I would say, in general, a state that has persistent energy and particle currents in there. So a classical example is something like I have a hot plate and a liquid on top, and I'm cooling it from below, so the energy flows through here. And this is also an example that shows you that in such a dissipative-driven state, you can really get interesting things like pattern formation or non-trivial limit cycles and so on and so forth. Yeah. Now, in the beginning, I said that like what I'm interested in is like relaxational dynamics, not driven dynamics. So you can ask what's the meaning of the driving in this situation. And I think what I have in mind here are like, as I said, transient quasi-steady flows that emerge because energy or particles flow between different subset of degrees of freedom. Yeah? So for instance, let me go to this photo-doped state, which I already draw, where I have particles up here. So the relaxational dynamics will be that these particles go back by recombination. The energy goes to somewhere else, phonons, magnons, whatever. And if this is a slow recombination current, I can think of this as I can think of an approximate like stationary state, which really describes the same physics, which would be one in which I put some reservoirs here that slowly pump in particles, and a reservoir of like a lead. This can be metallic leads, kind of which have a voltage bias that pump in. So I have a current that goes in the system, recombines, and goes back out here. So then I have a quasi-stationary representation of this. Or I can think of this energy, which is actually passed on, goes to some other subsystem, and from there maybe to the lattice. And these other subsystems could be magnons or like plasmons or plasmonic excitations. And then you have this subsystem, which is actually strongly driven. And there are nice proposals, like, for instance, by Andy, that you can have a magnetic subsystem that actually evolves into a steady driven state, which can be very different from non-equilibrium state. There's actually another type of dissipative fixed points, which I found interesting, which is probably not so relevant also for this community, which I just like. And this is such states that are related to turbulence. So turbulence is also kind of a dissipative state, because when you try to push flow through a pipe, you actually apply perturbation to the system on a large scale. And what the system does, it forms vortices which break down to smaller vortices in a cascade until the smallest vortices eventually like dissipate the energy. Yeah, and so this is a steady state energy flow which goes from large scales to small scales. And although each individual trajectory of the liquid will, of course, be chaotic, like if you look at something like the momentum distribution, this will, can in some cases actually form a steady momentum distribution, which has a universal form, such as a power law, that's really different from a Bose-Einstein distribution. Yeah? And there are some proposals that, for instance, if you prepare a non-equilibrium distribution in a Bose-Einstein condensate or quantum, like a superfluid liquid, for example, a very non-thermal distribution function, then during the relaxation, the scattering of particles will actually transport particles to higher momenta and smaller momenta, and what emerges on a transient scale is such a universal distribution function. So then really you have also a quasi-stationary situation which can be nearly described by a dissipative state. This has been also called non-thermal criticality. As I said, I don't know whether there is any relevance for this or any manifestation of this at the moment in condensed matter, but I just wanted to flash it also here. In general, I think I will not say much about these dissipative driven states later on, but I just want to mention that if you really look what kind of true non-equilibrium steady state phenomena there are, like self-organized patterns, as I showed, like limit cycles, or these states which Dieter Jaksch has shown that you can stabilize other phases by dissipative driving protocols. I think this is something that definitely maybe should be more explored, like whether in transient steady state situations we can also have such quasi-stationary non-thermal states.
May I
yes.
ask a question just in terms of this classification? Is it interesting to think about all of the active matter stuff that we hear about from biologists and soft matter physicists in this context?
Maybe,
I mean, there's
yeah.
Quantum, but there is quite a lot of discussion now of basically dynamical states under drive of various kinds.
So active matter in the sense that really there are internal degrees of freedom, which can provide.
There are two kinds. I mean, this is. I don't want to take up too much more of your time, but there's one kind where indeed each particle has a little internal energy source and its own dynamics. But the other thing is just matter with some kind of internal structure then under a current flow or something like that. You have these polymers or pneumatics and that. And once they're under flows, they organize in interesting ways. And then related in the purely static sense, but non-equilibrium is the whole business of self-organized criticality and sand piles and the jamming transition and all that stuff. Anyway, I was just wondering from your point of view how you think we should fit this into this.
Yeah, maybe that's probably also because that's in principle this is also like classical. Of course, turbulence is also a classical, but it's like a self-organization or like a universal form in momentum space, and then you can ask whether you have similar structures in real space. And that's what I meant, like when I, for example, show this like self-organization under driving classical systems. I'm not aware of a good situation in a pump probe or ultra-fast experiments where I observe such a phenomenon, but maybe it's worthwhile thinking whether there is such a situation that the steady state drive, for instance, which emerges, what is like, if I go back, this steady state drive can actually lead to some self-organization in a subsystem on a certain time scale. But I'm not aware of a situation that does this at the moment. Maybe some is in a clear sense.
Trial at different time scale, making these hydrodynamics and turbulent flows in Corvino, these Corvino two lines that you move one internally rotating and the outside one. This is the way it's been used to study turbulence in classical hydrodynamics. And this has been done now for studying transport in nanostructures.
Okay, that will be interesting, yeah, if you show more.
And the other thing is the stuff that I heard about from Peter Blue, and I don't know how real it is, but that the driven exciton polariton condensates. There's this whole business of transitions associated with exceptional points in the presence of a drive. Yeah,
but then it's probably a real driven steady state, yeah. And now I was wondering whether you get this as a transient quasi-steady state somehow. Anyway, there is a third class and of, okay, I'm going back here, of like non-thermal type fixed points, which I'm not sure whether I call them, but clearly they go into this business, which is classical metastability. And we had a nice talk by Andy on this topic, so I don't have to say too much about it. Like classical metastability means that now the steady state is a minimum of a classical theory, and the classical variable that we talk about could be, for instance, the order parameter as a classical variable. And that, as I said, we had a nice talk. We just summarized some questions that come up. So if you have such metastable minima in the problem, the system, the main question is like how you end up in there. And this is what, if I say this again, part of Andy's talk was about, that one possible generic mechanism that really one phase might be thermodynamically less stable, but still the dynamics of this phase might be faster than the other phase, so that if you prepare an excited state, you can end up in this state. There's a related way formulated, which can have two order parameters when that are coupled. I can imagine that one of them is like more robust than the others if I thermally excited, like go up in temperature, but it's less robust against excitation that are imparted by a laser pulse. Yeah? And therefore, I can, on a short time scales, like control these in a different way. And here, I want to show a few results from like from an older work which we had ourselves before continuing this list, just to illustrate. This was for a 2-orbital Hubbard model. So you can view this like you have two degenerate orbitals, which can be EG-type orbitals, and you have one electron here per site, and it's in the Mott regime, so charge fluctuations are suppressed. So these two orbitals form an orbital doublet, or like a pseudo-spin, and then if you just have the electronic model, so just electronic super exchange, the order which can emerge will be one in which, for instance, you have both magnetic and orbital order, where kind of here you have ferromagnetic planes that are antiferromagnetically coupled, and the orbital here forms an antiferro, so staggered pattern. So in this orbital pseudo-spin picture, like on one sublattice, you have here this polaris orbital pseudo-spin, on the other this moment. Yeah? And then you can draw a phase diagram where this is the x is the orbital order parameter, the s is the spin, and as a function of temperature, you follow the trajectory in this phase diagram. So you start one in which both orders are present, and then they are both suppressed, but as you can see, the magnetic order in this case is actually less robust, so for high temperature, retain purely orbital ordered state. So now you can ask what happens if you excite this, and excitation is really a laser that creates such charge excitations, which are then mobile and can move around. And then you can, this is an actual simulation of this Hubbard model on short time scales, so you can view this more like femtoseconds. And then you can follow the different order parameters, how they start to decay. You can extrapolate this somewhat to longer times, because the actual numerical simulation doesn't allow you to go further. And then if you extrapolate this, you will end up in this diagram an extrapolated state in which spin and orbital order are not along these thermal trajectories. Yeah? And depending on the excitation you impart in the system, you move along another trajectory. So it's really one of the situations where, at least on these electronic timescales, really the dynamics gets you to a non-equilibrium state. And one interpretation, like a simple like hand-waving interpretation, is that these carriers which move around like in an anti-ferro background, so if these are like the orbital pseudo-spin background, if any hole or whatever moves in an anti-ferro background, it leaves always behind a string of defects of this order, so it can very quickly destroy this order, while when it moves in a ferro-ordered background, and basically it does not disturb this order, and this is why the order, which is actually more robust under thermal fluctuations in this case, is quickly destroyed by the photoexcitation. Yeah? So it's one like microscopic example of these mechanisms where the order parameters behave different in dynamics than in thermal. Okay, but with this, let me go back to the list of questions. So this was possible ways to end up. Then the question that was highlighted by Andy times is a question how you actually get out of such a minimum. And one question that I would like to ask is also, which as turns out related, is what's the role of such spatial fluctuations? Because the order parameter is not a homogeneous quantity, it has spatial fluctuations. And okay, what this means is you can create defects, disordering, and a defect is nothing else than another like local minimum of your classical theory. But it's a local minimum which actually, in contrast to this thermodynamic minimum, has an energy barrier, which is microscopic, okay? And therefore, the escape from this local minimum will happen by like stochastic fluctuations, so thermal fluctuations, or also possibly by quantum tunneling. And these are timescales which can still be very long, so you can still be trapped for long times, and they can therefore be very significant for the dynamics. And yeah, so it's really the question whether the formation of such metastable, of such inhomogeneous disordered states or metastable domains is relevant and influences the dynamics of the symmetry broken states. This is actually what my talk was supposed to be about. I hope I come to this in the end of this tutorial. Yeah, and actually also the escape from the thermodynamic metastable state always appears via nucleation and growth, so you have to form these defects in order to escape, because the thermodynamic barrier you can never cross by fluctuations. Okay, so now, how much time did I use for this roughly? 25, okay, I should probably go quickly over this so that I can spend more part on the other one, because now I had a bit of discussion on this photodoped states, yeah, as an example of quasi-steady states. So let me just go through anyway. So photodoping, as I said, means that you laser pulse transverse electrons over a gap, and then usually you have certain relaxation processes that set in, which you could classify as like electron-electron scattering or relaxation, passing energy on to bosonic excitation, spin, phonons, and so on. And you can classify them by like everything which is intraband, which keeps the number of carriers in the band constant, or interband relaxation, such as the recombination, in particular of electron and hole, where the energy goes either into exciting other carriers which are around or into a bus. So whenever you go to a semiconductor, large gap semiconductor, I mean, these time scales are very clearly separated. All interband scales are very much faster than these recombination scales because of kinetic constraints, like the large energy which is released by recombining electron-hole pair has to go to many bosonic excitations or has to be distributed among many other particles. And this is a kinetic bottleneck. And that means for times which are well in between these intraband and interband times, you'd expect that you form a quasi-equilibrium state which is only controlled by the number of excitations which you have. So you can describe it more or less by two Fermi functions with a separate chemical potential in the upper and lower band. Yeah? And the temperature is set by, say, the lattice. That's very well known since the 70s. I mean, work of Keldysh and others. And I think in semiconductors, this lifetime can be very long. So if I understand this correctly, sometimes you can even take a photograph of such an electron-hole droplet in semiconductors. Now, what we were mostly interested in here is what is different if I do the same thing for a correlated system. Yeah? Because in a correlated system, it's the gap itself is opened by the Coulomb interaction. And the same Coulomb interaction is relevant for these scattering processes. So you can ask, is the bottleneck still active? Also, in such a correlated system, the quasi-particles which you have are not really robust, well-defined quasi-particles for which you can easily write down a kinetic equation. But yeah. And the last thing is you are strongly coupled to spin degrees of freedom, for instance, which have itself a relatively high energy as compared to phonons, and they could provide a much more efficient mechanism to release the energy. Yeah? So the question is whether in this case you would not expect that on much faster time scale, the whole system actually just forms a hot electron state where the electron itself have one temperature. And this is something which has been investigated a lot. Here I have a summary of the work which is related to the one which we have done ourselves using this so-called non-equilibrium DMFT as a means to actually solve the time evolution of correlated electron systems. And in this talk, I don't want to say much about methods, of course. So in this single band, Hubbard model is minimal model for the Mott insulator, where you have a metal at small interactions and the Mott insulator at large. If you go up in temperature, this becomes a crossover, where in this region in particular, you have no well-defined, no Fermi liquid, no well-defined quasi-particles. And then you can think of preparing a state here, exciting it, impart energy in the system such that if it would go to a thermal state, your temperature would be somewhat up here, and ask what's the time scale for thermalization. And this is what has been done, and where you really find that indeed, if you are in this crossover regime, you have a thermalization on very fast time scales, so basically a few hopping times, which would correspond to a few femtoseconds, while as soon as you open the gap, indeed, there is this exponential bottleneck still present. And then in this regime where you have this exponential bottleneck and this long lifetime of population in the upper band present, you can actually start to do simulations in the presence of like heat bath, other degrees of freedom, and then you indeed also for these systems find situations in which you have this separate Fermi function in the upper and lower band. Yeah, so this is this picture kind of is valid. Let me switch over this. There's a few comments on this, but let me just be fast. So in this very fast thermalization in the bad metallic.
Just one curiosity. For these simulations, when you get the two Fermi Dirac distributions for the upper and the lower band, do you get them at the same temperature?
Yes. So this is, okay, why doesn't it go on? Actually, yes. So they are at the same temperature, even if the system is unbalanced. So for example, if I have in the beginning, I start from a slightly doped system, then these two chemical potentials are, of course, not symmetric, but still the temperatures of the team turn out to be roughly the same, of course, within the numerical accuracy. I mean, you have to simulate, the simulations have to go to relatively long times, so these are then hundreds of hopping times, so these are more challenging simulations, so that's why the explicit demonstration of this is also a bit new here, but it's also the state itself is also interesting. So the spectral function is strongly reformed. So you have hole-like and electron-like quasi-particles, which both give rise to some quasi-particle peak in the spectrum at the same time, which is a bit unusual. But this is result.
Energy exchange is very fast.
Yeah.
Particle exchange across the gap is slow, but energy exchange is very fast, so it goes to the same temperature.
Yeah. The question is like how efficient actually the energy exchange to the bath becomes. And they can also be regions where once this Fermi liquid is formed, the efficiency of energy transfer to the bath also changes. This is something which I think we have some indication that there's some slowdown happening in this, but I'm not sure to what extent this is really something I would to trust the numerics or what is due to the modeling and to the approximations used. But I think this is a bit of an open question, whether like once you form such a low temperature Fermi liquid, whether like it's another slowdown because you kind of can more or less decouple things from the bath in some sense.
So there's no bottleneck for exchanging energy between the upper and lower.
Yeah.
There are strong scattering processes which scatter two whole states amongst each other and scatter two electron states amongst each other. Exchanging particle numbers is a different matter, but energy is easy to exchange across the gap, as it were.
The reason I was asking is because in the ultra-fast community, when they do these two Fermi level models, like holes and electrons, there is a big debate about whether the upper part of the electron is a different temperature than the lower one.
Okay, that's interesting. Yeah.
They do it for these surface states and edge states.
Yeah. Okay.
And I never understood whether this was an efficiency of the model or the fact that
okay. Yeah. Oh, here,
getting the same temperature.
Yeah. Here the temperatures are the same, and as Andy says, they are the same, even if they are not yet the same as the bath temperature. Yeah.
This makes sense.
Okay. So then, okay. So in real materials, actually, the time scale. This was what I said here. So there's also this hot electron state, which like when the electrons thermalize, they do thermalize sometimes fast enough to do this at frozen lattice. So this can be also an interesting way to learn something about the system. And there's the work, for instance, by Newgetic group, a more recent one, where like the photo-excited state in a strontium iridate is really interpreted in terms of a thermal state, but in order to explain this thermal state, you have to say that this is you have to invoke a role of antiferromagnetic correlations. But anyway, so the hot electrons does not mean non-trivial in correlated systems, but anyway. And the real time scale for that in real materials, of course, the Hubbard model maybe doesn't tell you the full story because there are recombination processes active via spins and sometimes phonons, but in many materials you find timescales which are of the picosecond time, which is actually much, much shorter than in semiconductors, which is why this the physics has been in the early, has been called like ultra-fast like recombination, the same which we from the theory perspective call long-lived state, yeah, has been called ultra-fast. But still several picoseconds is enough to think of actually the question whether you can understand this in terms of quasi-steady state. And there's actually then the question comes, can you really prepare this quasi-steady state directly without going to the pain of simulating the time evolution? And there's two approaches to this, which go back to what I said in the beginning. One, you can understand it as this pre-thermal fixed point. And this is a work by Yuta Murakami and also Andy is on this, where you say like in this Hubbard-type correlated models, what the pulse does is create such doubly occupied sites out of a Mott insulator. And what is almost conserved is actually the number of these doubly occupied sites and holes. So what you should do is you should write an approximate Hamiltonian that conserves these. And this approximate Hamiltonian is a generalized TJ Hamiltonian, which has spin exchange terms, T squared over U. It has the motion of these charge excitations. And it has exchange interactions of doublons and holes themselves, which are also super exchange types, TJ over U. So, and then you can solve equilibrium states of that. And the other perspective of this is to view it as a dissipative steady state, where you really put reservoirs and study this dissipative flow and stabilize the distribution up here using reservoirs. And the nice thing is, when you use this to study phase diagram, actually to give this similar and consistent physics, yeah? So at least qualitatively. So, and the physics you expect is just one instability that you can expect in such a system is a eta pairing type of superconductivity, which is also being discussed in the talk by Dieter Jaksch, which you can understand best by saying, okay, if you just look at these charge states, they also form a pseudospin, charge pseudospin, and the super exchange interaction is and this kind of the up and down correspond to doubly occupied and empty, but the kind of eta plus and eta minus are actually pair creation and pair annihilation operators. So if you would have an order, there's this super exchange. So if you have an order of these spins, then it corresponds to a superconducting condensate. Yeah? And then if you scan the phase diagram, it's a function of temperature. That's rather inverse temperature, so here is low. And the doping, photodoping, so the number of doubly occupied carriers. So everything is half filled. So 0 means basically just spins. And 0.5 means I would have created only doubly occupied sites and holes, like everything else is no spins. And then this steady state formalism indicates some region of eta pairing stability here, which in the large doping regime you can really understand from this pure pseudospin model. It has been done by Achim Brosch. And in a 1D model, sorry for being a bit short here, this has been studied using this TJ model by Yuta Murakami's work, where you also find a quite extended region of stability of this phase under photodop. So this is what I wanted to say about these photodoped states. As I said, just a brief overview. So to summarize this part, so the lifetime of carriers in these Mott insulators is much shorter than in band insulators, but still like enough to maybe think in terms of this as a quasi-stationary state. And at least for the single band model, this pre-thermal and stationary non-thermal fixed point scenario are consistent in the way that they both indicate a range of stability of superconductivity. Of course, the question is here, is that still, like, can you reach this in a real system? Because the doping, you have to reach this high doping level and also relatively low temperatures. And also there are, in particular, this eta pairing, I have definitely not put all references there. There's nice work by Andy and Kaneko-san asking like whether you can also reach this eta pairing directly by imposing a pulse. Yeah. And there's subsequent work which also study other ordered states in this form, which I also did not go through here. And relevance to experiment I already asked. And then, of course, this is still transient. So you would now have to understand how to couple such a state to the lattice, for instance, to understand whether there is a true metastability. So, for instance, like, again, taking from Andy's talk, so you see when I said there would be one person in the audience who is more suited for me to give the tutorial than me, then obviously I was referring to you because I'm always referring to your works here. So here, basically, this is a state. All these trajectories here are actually photodoped states. Yeah? And if you wanted to really go to long times, we have to understand how to actually not just prepare stationary states in the theory as I have shown you, but to actually couple them to the lattice and go on with the dynamic. So now probably I have not, okay, what is the time? 40. So then, as I expected, I skipped this part because there was another question whether if the gap is opened by symmetry breaking, and then basically the dynamics kills the symmetry broken phase, then this leads to a very nonlinear dynamics. But I think Marius, who is not here, but he will probably be here in the afternoon, will talk a bit about this. And with this, I would spend the last minute on this, yeah, because here really the dynamics actually can lead to a sudden avalanche-like collapse of this gap, which stabilizes, and this is some. Yeah. So the last question is really on this disorder, which is induced, and this is some slides here. This is the talk which I submitted, and this is the work by particular Antonio Picano, who was a PhD student in Erlangen and now moved to Paris, and Francesco Grandi, who is now postdoc in Aachen, and also together with Chai-Chung and Philipp Werner, who is also well known here, I think. So the question is really, if I have a symmetry broken phase, like a charge density wave, the laser pulse comes, can quench it, and then it comes back. So we want to understand this dynamics. And so for experiments, for example, this charge density wave in the tellurides, like this is, at least qualitatively, this dynamics can sometimes be understood in this Ginzburg-Landau scenario, where you have an order parameter free energy surface, and then this order parameter moves in the free energy surface, can oscillate, and then relax back to one of the states. Yeah? And now I'm asking here, actually, what's the role of fluctuations of this order parameter? So, because it's not a homogeneous quantity, but it's like has spatial variations. And there's actually two ways in which you could discuss this. One is the limit of weak fluctuations, which you would discuss in a Ginzburg-Landau scenario using some so-called Gaussian approximations, where some main physics can be that the pulse can create a lot of non-thermal fluctuations, and these non-thermal fluctuations actually act back to renormalize the free energy and therefore change the dynamics. There's a work along this. But then there's you can even ask for having very strong fluctuations or strong variations, which can be understood as defects in homogeneous disorder being generated by the pulse on short timescales, and this can have also profound influence in the dynamics. And this is what we were interested here to study in a very simple microscopic model. And this simple microscopic model is a Holstein model, where basically I have tight binding electrons that couple here to at each side to a local oscillator, like an Einstein phonon. And if you study this on a bipartite lattice, then it wants to undergo symmetry checkerboard ordering of the phonon displacement and therefore also the charge. And this is a nice second order phase transition. And also goes along with the opening of a gap. So, okay. So if you want to study the dynamics, one thing you could do is you can, for instance, just say I'm decoupling the electrons and phonon and doing something like a semi-classical description. So I have the classical equation of motion for the phonons at each side, where the force is like the restoring force of the phonon and the force coming from the electronic density to which the phonons couple. And then you go on and say, okay, I'm just interested in the coarse-grained order parameter, so I assume that this displacement is the same on every other side. So then I have just like one displacement for each, and then you add some way of describing the electronic dynamics, which I'm not being very much detailed about here. It's some DMFT. And then if you do this after short excitation, you really see the excitation is weak. You oscillate, and you start with the displacement here, you oscillate around like a slightly displaced minimum. If the excitation is strong, you oscillate really around the, basically, yeah, I have it here. The simple picture would be you oscillate around the minimum at 0. Yeah? Okay, this is this picture which could be understood in this Ginzburg-Landau scenario. But now we can ask, like, can we not just allow the same here to break this translational invariance and actually allow to have each side here to have its own like displacement, and that also means that the electronic density has to vary. Yeah? So this is more or less what you would do in molecular dynamics, if you like. So one way to do is to assumption that you could do is that you keep the electrons in thermal equilibrium at each stage. And what we wanted to go here is like go beyond this. So we try to simulate the electronic dynamics in this context using so-called quantum Boltzmann equation. And the second and more important part here is that you want to go also beyond this simple Ehrenfest dynamics, because here the phonons are just driven by a force which is given by the mean field expectation value of the electrons. Yeah, as I said before, but we want to add some stochastic force to it, because if the electrons interact with the phonons interact with the electronic density, the correction to it is they interact with the electronic density fluctuations in time, and that correction corresponds to a stochastic force. So you can, and then you have to write a consistent damping. And what we try here is to actually extract this stochastic force and the damping from the electronic non-equilibrium evolution here. And then the whole thing is solved in a very simplified lattice, which makes it possible, namely the beta lattice. But then you get these results like this, where this is just equilibrium. And you have on this bipartite lattice some sites on each of the sublattices, and you look at the trajectories at each site, color-coded, they all fluctuate at high temperature. If you go to low temperature, you have ordered state where like each of these columns, here, these rows is a trajectory, so they would all be displaced in negative and positive. And so this is actually, if I average here and here, I get this second order phase transition. And now we can actually do dynamics. So we suddenly excite the electrons by creating population in the upper band. And then also the electrons are coupling to some dissipative bars so that they put the energy back on some time scale, so the distribution relaxes back here. Okay, it's a function of time on a picosecond time scale here. And then you can look at the order parameter, which is this black curve here. So you start from something which is displaced, and then the order parameter is quenched by this process. Yeah? But then you look at longer times, how it comes back, and here's the interesting part comes. So it's quenched on short times, and then it comes back. But then you can, at each of these times, look at the actual distribution function of the order parameter. Yeah? So you basically look at the like histogram for displacements on all sides of one sublattice, and here in the ordered state, it's clearly centered around 0, around the displaced state. Then once you quench the order, it's basically centered around 0, so they fluctuate wildly. But then the point is, if you come to this point here, where the order, mean order has not been restored, you see the bimodal distribution. So basically they already know that where they want to go, but they're displaced, but they're randomly displaced. And then as the dynamics goes on, kind of they sort out. Yeah? So say this is on, if I make a cut on the basically A and B sublet is randomly displaced, and then they sort out. Yeah? Okay, so this would be the hallmark of what is really a dynamics that undergoes via some ultra-fast disordering mechanism. Yeah? So you could view then this intermediate state that really here there are some sites which are on one sublattice, but they have the wrong displacement, but they still have a certain metastable potential energy minimum here, of which they can escape only by these stochastic fluctuations in the dynamics. And now I guess my time is up. So if you want to know more about a more precise discussion about this mechanism, we can discuss, because this is more or less basically, as I said, like one wrong displaced site can actually form a local metastable defect here. So it's this local stable effect here. And then let me rather leave the time for the discussion. Okay, so in this last part, I've shown you some microscopic simulation that actually gives this ultra-fast generation of disorder, which can be understood in some metastable defects and which have really an effect on creating a very long-lived dynamics in this system. Yeah, and of course here again the question would be to take this to more complicated, more interesting systems rather than this Holstein model. Okay, thank you for your attention.